discussing a paper out of the MIT economics department, Aidan Toner Rogers. The link's in the show note. Aidan's paper discusses a study where he's trying to assess the productivity of scientists that use AI. Now, here's why this is really crucial. I think this is one of the most important papers, at least in economics, that I've read for quite a while. First, of course, it's an interesting question, right? How is AI improving scientific productivity? But more importantly, like when we look at companies like NVIDIA, for example, or other tech companies that are heavily investing in AI, including, of course, Tesla and X and so forth, the question always comes up, well, I mean, is this overvalued? Is this, is this, I mean, how does this even make sense? We have 3 trillion market cap for NVIDIA, 1 trillion for Tesla and so forth. And I think the big question, the big question is not necessarily, does this valuation make sense? Because who cares what the valuation is? The valuation is the result of something else. And that something else is, to use a more fluffy term, is value creation. A more concrete term, it's actual profits, cash flows, numbers, right? So how is a company like NVIDIA going to produce the kind of cash flow that is necessary to justify its valuation over the long time? And I think the way we think about this here at Orange Capital Partners, we paraphrase Peter Thiel here, so credit to him. In 0 to 1, he talks about, I call it the P times Q concept. It's very simple. P is the value you create, P is the value you create for society, right? And Q is the value you capture. Now, P better be much larger than Q, first and foremost. Otherwise, you're not going to be tolerated by society. Let's say, I don't know, health insurance companies create more value for themselves than they create for society. The US government creates more value for itself than for society, so on and so forth. That's why they're mistrusted. That's why we don't like them. Wall Street, all of these, that's not okay. The other way around, we have companies like Amazon, NVIDIA, and Tesla, and many others, smaller ones, that actually do create a lot more value for society than they create for themselves. And that's why they're tolerated. They might not be tolerated by Elizabeth Warren or Bernie Sanders and so forth, but who cares? I mean, those are just, demagogues. What most of the public sees is, I don't have a problem with Amazon. I don't have a problem with Jeff Bezos, hanging out on yachts and having fun with sex models or whatever, because Amazon's creating a lot of value for society. And even though I'm jealous and envious and all that, I tolerate people like that. And when we talk about this, of course, this is a general sentiment. This doesn't mean everybody thinks like that, and I wouldn't want to put words in anybody's mouth, but overall, this is how we think about it. So anyway, back to this paper. The reason this paper is so important is for a more, let's say, macro reason, we want to understand, okay, look, is there actual value creation in the real world at work for people? And science is a really important part of work because, as opposed to maybe, I don't know, a bank teller at a bank or something like that. I mean, not to demean other people's work or anything like that, but science creates new technology, creates new value creation, creates the fundamentals of new value creation that then again can compound knowledge and even generate more wealth. And I think that's why it's really crucial. So anyway, so this paper talks about this. The findings of the paper are that we have an increase in productivity. We have an increase in particularly in 3 things. We have new ideas, we have new technological concepts, and we have new products. And this all should lead logically to also better value creation, more innovation. Importantly also, he states that it is the upper tier of scientists that benefit most from AI. And that's an interesting finding that is orthogonal to other findings that I've heard, where it's more the other way around, that the lower end gets a boost from AI And I want to discuss this a little bit also. This is not even on podcast. It's December 6, 2024. This is Krim Dalko. For the data, we're up 1.2%. The market's up 30 basis points. For the year, we are up roughly 79%. The market's up 27%. We're up from about 52%. So artificial intelligence, scientific discovery, and product innovation, the paper by Aidan Toner Rogers, MIT Economics, links in the show notes. Aidan discusses the productivity of material scientists at a company. So he has a sample of about 1,000 people. This must be a large company. And he has a couple of interesting, technical aspects of how he does the study, which is not going to be a part of this discussion. We're not an economics podcast here. But just to say a few things, of course, if I look at, let's say, okay, what exactly is material science research in the first place? I have to define that. Some people could be working on things that aren't necessarily research. Others could be doing a lot more fundamental research. So maybe the outcomes of the fundamental guys could be, and girls, could be less productive because it's more fundamental. So you have to be very careful in the way you structure a study like this, like everything else in economics. Garbage in, garbage out, of course. But I think the study is very well done. I mean, this is a professional economics kind of study, and he goes into extended length on how he does it, lots of references and all that. So my point is here, I would trust this study as far as the way it's done and the way it's being, the way it has been conducted, and also its findings really have some relevance. Now, for example, if you want to look at how is AI enhancing material science research, well, you have to ask yourself a couple of questions. One is, well, what exactly is the AI, and how is it being used in material science research? He explains that actually really, really intuitively. For example, the way material science people use AI is they first pre-train a model based on the idea. The fundamental problem is inverse material design. So you start with the property. You want to have a battery with longer range and higher energy density and faster charging. So you want to have those properties. And now you want to find the compounds that might be best suited for a battery like that. You want to have a material that you can inject into a human skull, let's say if you're Neuralink, that is conducting electricity really well, that is not heating up, and that has no immuno response by the human, and so on and so forth. You put in the properties and you get the design. Of course, we're pretty far away from having this type of inverse design all done in virtual reality, and then maybe last step we just tape out and go to the factory, kind of like how Jensen Huang once a while ago talked about drug discovery. He said, to paraphrase, I was the last engineer in my generation of chip designers who was actually in the lab. Today, chip design all happens in virtue, and then the tape out happens, and then hopefully we have everything right, and if not, we have to readjust the tape out and go back to to the factory and stuff like that. Now, that could be happening also in many other areas where physical products are being designed. So this is fundamentally the idea here also in material science design. So we use AI to first, so that's the goal, right? The goal is inverse material design. We start with the property, and the AI gives us the compounds that we need. Now, how is this going to happen? Well, first we need to feed the model something. What we feed the model is data, and the way we pre-train it, we have certain compounds and certain properties. So there's a lot of stuff known throughout 200-300 years of research, maybe even more, but definitely since sort of the Enlightenment, alchemy, and then chemistry and physics. We have a lot of knowledge about how stuff behaves, and we can sort of we can train we can train these, we can pre-train the models. Then we have fine-tuning. So now we can say, okay, look, this is akin to AlphaFold, right? We have I think AlphaFold was trained on, I believe, about 100,000 known structures of proteins based on its amino acid sequence. So we have done a lot of groundwork understanding the relationship between chemical structure and function. Let me quote from the paper. Traditionally, scientists discover materials through an extensive and time-consuming system of trial and error, conceptualizing many potential structures and testing their properties. The AI technology leverages developments in deep learning to partially automate this process. So what is he saying here? Like, scientists go to the lab and think about compounds that they could be using, and then test their properties, and then go back and forth and iterate until they find something that could be useful to solve the problems. How can AI technology partially automate this process? Well, he's saying the way it can do that is it can help you suggest compounds. So you can run a model, give it, ask it, look, give me a compound that has higher energy density in a battery. And it suggests compounds. And then you, as a scientist, you can go and try it out, and maybe, go back to the model, interact with the model, say, look, I've tried this. It's not really working very well because X, Y, Z. What do you suggest? So there's this potential for an AI-assisted scientific research agent, if you will. And I think this is really, really exciting. And I don't think this is hot air at all, because if you look at the workflow of a scientist, she really has to do a couple of things. She has to iterate, she has to try stuff, and then improve. And there's a lot of that work is kind of tapping in the fog of high dimensionality. So there's a lot of also streetlight danger here, that we might just be tapping in an area that we know, and maybe we should go, move 37 in AlphaGo, where let's try something completely crazy, right? This goes back to Chris Ree's essay about axiomatic knowledge. Like, how about, we have a highly dimensional space of compounds, of potential compounds, and maybe these models can iterate over many, many dimensions and give us predictions that we humans, just because of our axioms, because of our inductive biases, don't even try, because it's just too much, too many potential outcomes and things. So there, I can see the potential. So what Aidan's doing is he is evaluating these models, and he is looking at how are they actually really helping. And he finds out that they're incredibly helpful in the first phase, which is the sort of try and error of compound prediction. And he says that in particular, top scientists, this is really an important finding, the top scientists in the cohort are better at evaluating those predictions and using them downstream for tape outs and eventually produce new materials. So this is kind of, think about it this way. Like, if you're an experienced hiker, right? You really are experienced in the Sierras. You live in California, you hike the Sierra Nevada every spring to autumn. You will be a much better user of any kind of weather prediction model that's out there, because you also have domain expertise, right? You will know that, well, this, clouds in July on the eastern side of the Sierra really don't mean that much rain, and the rain isn't so bad, so I can still go on hike. Or maybe a certain height will save me from the fog, or stuff like that. Like the more expertise you have, the better you can use the AI prediction models. What is the AI really doing? The AI is going through a multidimensional try and error space to give you suggestions. And if you have enough domain knowledge, you can use those suggestions to your benefit and really produce better results. This is the key finding of this paper. I don't want to boggle down too much on the percentages. He talks about 40% better innovation, 20% more products, whatever it is. Look, let's think about it this way. Imagine if we could have a 20% more 20% more innovation in the material science domain of technology, which is sort of the base. First, you got to have the material. Then you build technology and systems around it. And then you actually deliver applications. You can see that there's a compound effect here that, in my opinion, really could bring enormous economic growth. So I think this study, as important as it is for operations managers to understand how to use AI for their companies, this is also a macro. And now, let's tie it back to our purpose here as Orange Capital Partners. We're in the business of wealth creation, and we're investing in AI technologies, fundamentally new concepts, engineering practices for the purpose of wealth generation. There is some real tangible wealth generation potential here. If we could improve productivity by 50, 60, 70, double productivity in the, let's say, 5 to 10 year frame, that's huge. That's huge. That means real growth. This is Clayton Christensen 101. That's real growth. That's not Fed-driven investment BS, paper pushing type of growth. This is real growth. This is driven on the drawing board by technologists. It's just faster. It's more geared towards results. So we don't need a Thomas Edison, Nikola Tesla, Walt Disney, and so on. We can have a little bit more industrial, a little bit more engineering-driven scientific growth. Engineering-driven meaning it can be a little bit more structured. And it's not just this hoping for the lucky strike type of stuff. It's still there. Creativity is still there. What this also means is go study physics, study math, study chemistry, study physical chemistry. All these things still matter in material science as much as they matter in many other areas of engineering, because we're far away from understanding all these compounds and understanding all the properties. And I think there's a new discipline going to emerge out of this, which is sort of the scientists that trains models. I think there's going to be, sooner or later, a physics department somewhere, probably on the West Coast, that will have a chair, or at least maybe an adjunct professor first and then a chair at some point, that is building a system, building a whole knowledge value chain of how to train models to better be at material science prediction, better be at physics prediction. You could use that same concept not just for material science, but for physics in general. Particle physics, right? What kind of data do you have to feed a model so it can give you better predictions of, let's say, how particles behave? And you can ask that same question in almost any other field of physics and engineering. So to summarize, I think this paper highly worth reading. I just spoke with a material scientist yesterday, and he agrees. He thought it was very interesting. Does second some of the findings. Of course, the question here is, for example, how do you define top scientists? And the author actually goes again at length to define all these things. So I think he does a really good job. This is not just some gibberish, study like some of the AI ethics studies that are more political than anything. This is a real tangible study that actually tries to answer some really hard questions. And the findings are: AI increases novelty as measured by the difference in compounds discovered. AI drives innovation as measured by new technical terms used in papers, and AI changes products as measured by novelty of product lines introduced. Thank you.